All right, so in the first lecture, we went over Sweden's history, geological history, Stockholm's geological history, the main lithologies, and then I went through the ductile and metamorphic history in the second lecture and talked a little bit about sulfides there. And this last lecture is going to focus purely on the brittle deformation history, but mostly on different types of brittle deformation structures in Stockholm, because these are the most important features when it comes to building in Stockholm. And a lot of all the geotechnical aspects of Stockholm are mostly steered by this brittle deformation and the brittle history. Let's get started. The main thing that we're afraid of, let's say, in geotechnically speaking, rock mechanics speaking in Stockholm, when you're building a tunnel, is weakness zones. For instance, building a tunnel, but even building big open cuts. You want hard, less fractured rock that is stable and will hold up a slope or hold up the roof of a tunnel. If you get a weakness zone, that's not good. So it's good to know how they form, where they come from, where they might be, why they're there. But first you need to be able to describe them well. And there's different ways to describe them. And I've just shown three different sort of models of it. If we take the sort of SKB model here, they point out that weakness zones can have a transition zone. So this is just normal rock. They have a transition zone, and then they have a core, let's say. If we look closer into that, SKB has tried to sort of quantify that in a better way by looking at fracture frequency, fractures per meter. So there's the host, and then in the transition zone, let's say we have 4 to 9 fractures per meter, and within the core we have more than 9 fractures per meter. And even in the core, within the core, you even have fault gouges here. So even thinner kind of features. That's one way of talking about weakness zones. Another common terminology you'll hear in Swedish is spröda and krosszoner, so fracture zones and crush zones. And I really like this old sketch here that shows just sort of how they can look and what you would call a fracture zone versus a crush zone. The main difference here is fracture zones, you still have distinct fractures. They can form networks like here, often conjugate here, for instance. Think of a shear fracture here, you're shearing here, you have that X, like I showed before. And then a common way of thinking of a fracture zone is an increased frequency of fractures, like here, that are usually in the same direction. That's a typical example here, there. But you could also have a little bit more diffuse where you're starting to get a little bit of clay gouge. But when it comes to crush zones, there you have definite alteration along the fracture, a lot more alteration along the fracture, and you just crush up the rock. And so here's an example here of just fault gouge here. Here we have thin fault gouges and a lot of alteration of the rock around it, a big halo alteration. And if you look close inside of one of these little gouges, you would see structures that look kind of like this within the crush zone itself. What do these look like in reality? I'll just go back to this again real quick. If you notice here, the sort of SKB model is that you get a crush, typically get a weakness zone in topographic depressions or even water passages in Stockholm. And they always depict it with the weakness zone right smack in the middle and vertical. And here's a good example of why one should not assume that. Here was Hjulsta in northern Stockholm, where before they were going to build this big trough, they knew that there was a depression here in the bedrock. So you have to imagine that this is all rock that we're standing. I mean that this where I'm standing right now taking this picture doesn't exist. It was inside the rock. So all we knew was that there was, or not we, somebody else knew, was that there was a depression here. And so they assumed there was a weakness zone right here in the middle. what you can see, in fact, is that the weakness zone here is off on the side here. I think you can see this kind of a red altered rock here. And in this particular case, it was a big problem because they assumed the weakness zone was in the middle. They did all kinds of curtain grouting here on the back side to keep, so that when they did build this shaft, water wouldn't just drain, or it's not this shaft, but this trough, that water wouldn't drain into it. It wouldn't drain the wells behind here because there's a bunch of energy wells behind here. There's a whole neighborhood back there. But in fact, when this got blasted, then all the water came out along this weakness zone that happened to be on the side, and the grouting only went down to there. They didn't know about that weakness zone there. So, and this is a fairly common thing, that these weakness zones dip under higher topography in Stockholm and are on the edges. Another important thing to note about weakness zones in Stockholm is that, or anywhere, is that they are not just because you see it in one place, you can't characterize how it's going to be everywhere. And there's a lot of variation laterally. So here I'm standing in another trough on the right-hand wall side. I have this thin little structure here. This is less than 10 centimeters thick here with some alteration. It is an obvious what's called a slag in Swedish. Maybe you'd call it a fault seam in English. But if you look on the other wall, it's a lot more. It has a lot more scope. It's a lot larger, and it has affected the rock in a lot worse manner here. You see, it's all crushed in between. It's split into diverged into two zones here, and altered the rock quite a lot. So they can vary a lot. So when we're trying to find these weakness zones and investigate them and characterize them by drilling through them, for instance, with a drill core, remember we might drill through that and just see a little bitty thing, or you might drill through that and see a big thing. So it's sometimes good to drill 2 holes through them in different places. What do weakness zones look like close up? Well, they start off with a breccia here, which can look like this, with quite a bit of a chlorite infill or more fine-grained matrix, let's say. That then might get reactivated, and you get a chlorite seam down the middle here. And then that might get even more reactivated or hydrothermally altered, and it just becomes a chlorite-rich clay, which obviously building in this rock is not, this is like building in soil, almost. I have a nice example from a recent tunnel here of the other end of this diagram. So the breccia, before it even gets so altered that it starts to kind of look like this. I'll just show a picture of that with the camera. Here in drill core. Wait, I got one here. Here, a beautiful breccia with probably altered granite and pegmatite there. And it's cohesive. In this particular case, it was a very cohesive breccia, and I mean, it's perfectly fine to build in. So now I'm going to just show, so I'm moving away from weakness zones now, and I'm just going to show sort of what kind of fractures and fracture fillings we get depending on what age they formed. And I'm going to link it still to the sort of history that we had before, the history of the tectonic history of Sweden. We start out with the oldest, and I apologize for the blurry pictures in here. It's the best I can get. It's a great publication SKB publication by Bjorn Sandström, colleague of mine, where you can see the pictures better, but when you blow them up to this size, they get fuzzy. But the main thing to notice in the first generation is probably late Sphecophynian or Corellian, as some people call it, so 1.8, or it might even be, could be Gothian, or it might even be theoretically 1.1 GA. None of these fractures have been dated properly, really. So these fracture generations, so these are kind of based on cross-cutting relations and some other assumptions. They're characterized by brittle deductile cataclasites on the micro scale. They formed at over 200 degrees Celsius, and the typical filling is epidote quartz chlorite. Could look like that in the drill core piece. If you have a borehole film, might look like this. Note the very easy to identify green, kind of olive green color of epidote and quartz associations here. This is a generation 1 fracture in Stockholm. Generation 2 fracture is quite commonly seen where you form adularia, which is a special type of colorless to white K feldspar. It's often stained red. It's often not colorless in Stockholm because it's altered. We have submicroscopic hematite in it. So you get this kind of red coloration instead. Here's what it looks like in an electron microscope. This forms at around 150 to 280 degrees Celsius, probably Sphecondal region. These other minerals also are common. I mean, can form, but this is by far the most common one to see. If you see calcite and chlorite, it's going to be hard to know which generation because you're going to see later on that it's in lots of different generations. But I'll show typical examples of those. Also, as mentioned, during this generation, we have calcite, which you see here in white, and, well, some of these are calcite, and laumentite. Laumentite is a white zeolite. It is also often stained red. Again, these form at these same temperatures because it's this generation, same conditions. And we, again, get red staining of the whole rock. There's also chlorite involved here. Just more pictures of the same generation. This is one of the major generations of the fracture formation here. A little bit of prehnite here. Prehnite's really hard to identify. You have to be a specialist to be able to see it really in the fractures. Same with laumentite. Chlorite's a bit easier. It's this green, well, mica. Here's a typical fracture surface there where you have sort of chlorite combined with laumentite forming steps, the silicon sides. Here's this sort of cataclastic laumentite stained red, and then we have a later generation of calcite, probably generation 3 or 4, that's cross-cutting it. Third generation of fractures is a lot lower temperature. These are probably during Paleozoic reactivation, probably caledonide related. We have adularia, calcite, and quartz, and we have the introduction of a swelling clay in this, which is called corinthite. You don't really didn't know it's called corinthite, but there's swelling clays. They look like that in SEM. Again, quartz and pyrite get remobilized during this period. And then the final generation here, which is probably post-Paleozoic and possibly even quaternary related expansion joints. And it's a very common fracture surface you'll see are chlorite and calcite. This white cloudy stuff is calcite. The green here is chlorite. And then you can even get clay along the fractures. There's a clay-filled fracture here. These are often quite transmissive, these fractures, so a lot of water in them. And even these late fractures aren't always so consolidated. I've just shown you pictures of the nice minerals and all stuck together still. But a lot of times, here's a good example, a really special example from a drill hole film here, where you can see this is probably a soft calcite or a clay that's getting washed out by the flow in the fracture here. So this is a beautiful example of, I know that there is water flow in this fracture. because I can see it. It's in the ing, as we say. It's very rare you can see the actual process happening there. And so then we know that that fracture is definitely transmissive. Now I'm going to show some, that was sort of pictures from drill core of those different generations. And I'm not going to talk about those generations anymore and which mineralogies we have in it. I'm going to now talk about the kinematics of it and some sort of recent discoveries I've made. We go back to this picture again of the main ductile shear zones that always get reactivated, typically get reactivated as brittle weakness zones. And then fractures are also often in these orientations. And I'm going to focus on sort of east-westerly. First, this east-westerly sinistral zone here. This is a picture from Slussen again. And here I'm looking up at the roof. You see this pegmatite dike here that's been offset, dextral offset when looking at this. But you got to remember that you're looking up at the roof. If you were going to draw this on a map, it's switched. You project it down. So it's dextral. If we take a closer, we zoom in on this brittle shear zone, we see that it's basically a quartz breccia. And if we think of now a more larger, I didn't completely go away from weakness zones yet. If we take on a larger scale, which are the major weakness zones in Stockholm, the classic way of looking at this is just to follow the water passages. I mean, it's very easy to see these quite linear water-filled features. Obviously, the water goes into a topographic depression. Obviously, the assumption is that the topographic depression is caused by weaker rock. The assumption is the rock is weaker because it's been crushed up in a weakness zone, or a shear zone. All those assumptions lead to a map like this. This is modified from Bäckström and Cheng. It's a BFO report. Sorry to move that there. You can see the reference. And their assumptions are always, the assumption again, as I said, is these are subvertical or very steeply dipping, and that they're strike slip. And that's based on this idea of east-west, sort of roughly east-west compression, and that they were activated during that. And so a lot of these kinematics are based on that assumption, but they're also, in this paper, they back that up in a few places, several places, by looking at the kinematics along slickensides on fracture surfaces. They don't always are lucky enough to see the actual fault surface and look at slickensides on those, on the major faults, because these are rarely, they're not exposed on the surface because they're topographical depressions. So the only place you can see something like that, the real shear zone, is in a tunnel, and then it's very hard to have time and access to do such a detailed analysis of the kinematics. Or you have a drill core, and those things are so small, the surface that you get there is such a small surface, it's hard to do much kinematic work. But they did a pretty good job, and it's better than anybody else has done here so far in Stockholm. But this is their model that they've come up with here. Another model, or not, another way to think of this kinematically is to look at much more detailed studies done up in Forsmark for SKB, done by Mike Stevens and others, to give you a general idea of how these shear zones develop. Why are they in the orientation that they are relative to the compression direction? And we start with this earlier north-south compression from the Svekafinian. You get these ductile weakness zones here, and even then they have possibly some gently dipping reverse faults in between them. These are sort of space-making kind of thrusts. And you get things called Riedel shears, which you guys can learn about in structural geology. I'm not going to explain them here, but they're related to the same shear system. And then when you reactivate this in east-west, then you get the opposite shear sense here. This becomes then sinistral, for instance, and these get activated in the opposite directions. But still, note this gently dipping fault's going to be active also during this entire time. And that's mainly what I wanted to show this slide for, is to say, hey, somebody up in Forsmark said there's gently dipping thrusts up there. And I started seeing this in tunnel. I've been in the last 10 years of mapping in Stockholm. I've been seeing them more and more i.e. these weakness zones in the faults that are not just subvertical strike slip faults. Here's a good example from a tunnel here. This is fairly moderately dipping to shallowly dipping. It's obviously a fault of some kind. It's got a breccia in it. And there's even offset here. Here's some more examples. Here's a breccia that's looks fairly similar to the core that I passed around there and had up in the camera earlier. See the foliation bending into it. Here's another one with a nice bit of offset thrust. Here's another very shallow dipping. All of these are fairly shallow, are quite shallow dipping thrust here. Here's a little conjugate set of thrusts, showing obviously sort of subhorizontal compression here. And this is really important because it's basically never been described in Stockholm before. And so if we take this model of Backstrom and Cheng and the general geological SGU geological map here in the background, and we take some of the observations I've made in a particular tunnel here, we see that these, and we look at the orientation of these shallow dipping structures. I have not done kinematics on them always, just on those small fractures I've been looking at. But I just looked at which way are they dipping, what's the polarity of their dip. And interestingly enough, they're grouped. So you get north dipping, a group of north, a group of south in red here, a group of north again, and then a group of south dipping, shallowly dipping. And this kind of geometry or architecture of faults or weakness zones is what we call duplexes. So if I took a cross-section, now a cross-sectional view of this, it would look something like this here that I'm showing down here in the corner. You get these sort of stacked shallow features. And if they were thrust in this particular case, they would be pushing up the topography or pushing up the rocks. And that's a little bit of what we see here if we look at the south-dipping duplexes, that they roughly correspond with topographic highs in Stockholm. So this is a new thing I'm just now developing, like in the last few years, a theory of this, how it hangs with these other large, these blocks that are bounded by these sort of strike slip later, possibly later reactivations. We don't know yet. I have linked it. Oh yeah, I'll go forward. I have linked it with förbifart weakness zones as well. They also show, and this is very preliminary analysis of this, they show also these kind of groupings of switching north to south dipping. They're not quite as shallowly dipping there on this side, but the general pattern still holds. And here I've just kind of point out that if we start thinking of these faults as either thrust or reverse fault or normal faults, and we think of alteration, what kind of tectonic event might be responsible for this, you need to start looking at the alteration or any other patterns. For instance, if this is a thrust duplex, maybe these little northern faults, which obviously are not causing the big they are in topographical depressions, but they're not causing these major weakness zones, these thinner, more isolated, localized depressions. These were maybe back thrust on it, and maybe these are pop-ups. I don't know. I don't know yet. But what you can see is that it's more openly folded between the south-dipping duplexes. And alteration-wise, in the south-dipping duplexes, it's most common in the hanging wall in the north. Here it's on both the hanging and the foot wall. On the Slusen fault, it's in the foot wall, for instance. That's the fault here. And in the north dipping ones, it's there's not much alteration at all on them. And when it is, it's in the hanging wall. More commonly in there, you do have alteration, which means that they are it's these south dipping duplex faults which are the real heavy hitters when it comes to alteration and making major deformation zones. Apart from this big one here, in förbifart, which is actually north dipping and shallow. But you see it's a different orientation than the ones I'm looking at here, these east-westerlies. More information from one of my tunnels. where I have a huge data set of probably 10,000 fractures, 7,000 fractures measured. And these are fractures that are more than 3 meters long. And it's important to keep that in mind. I'm not talking about small broken up bits, short fractures. I'm talking about long fractures that cross a whole tunnel, for instance. They're always the most important when it comes to rock mechanics, because you can form large wedges that can fall out of rocks. Also, hydraulically speaking, they're the ones that are going to be carrying, they're able to transmit a lot of water. And I started looking at this data together and start seeing some interesting trends. First, if we look at the frequency of these 3 meter long fractures per 100 meters in the tunnel, and we see the highest frequency of these are in the altered rocks. That makes sense, because what is causing the alteration? It's this weakness zone, it's the shearing and things like that, and the hydrothermal alteration that's following the weakness zones. So that's not a huge surprise. What is a surprise, though, is that the Stockholm granite has a high fracture frequency of these longer fractures, not necessarily the smaller fractures, but the long fractures, continuous fractures. Much higher, in fact, than the sedimentary gneiss and the gneiss. The granitic gneiss is also similar to the Stockholm granite, but the sedimentary gneiss and gneiss, which is a majority of the rock in Stockholm, has a much lower long fracture frequency. And this goes counterintuitive to what most people think. They say, oh, it's a biotite-rich sedimentary gneiss, it's a weak rock. It's much easier, it's much better to build your tunnel in granite than it is in the sedimentary gneiss. That might not be true. It's definitely not true in this case. If we then look at the how much water these rocks are carrying, the different lithologies are carrying. Oh, wait, sorry. Before we go to that, also, it's important to look at which types of fractures are more frequent in the different rock types. And by that, I mean by which joint set or which orientation is more common. So here you see these on the left-hand side here, you see just some strike dip symbols. The longer the little line out from the strike symbol is, the more shallow dipping it is. So subhorizontal, shallow south dipping, like as part of those duplexes. And shallow north dipping, that one. And then these other ones are more steep. And what you see is that these shallow south dipping and these shallow dipping fractures are much more common in the altered red granite. Whereas the more steep structures are common in the altered gneiss. And some of them most of them are following the foliation, which is subvertical in the gneiss. If we look at the amount of water in the lithologies, this is a grouting fan. So a grouting fan is when you drill into the rock and you inject cement in there to try to block off water coming into your tunnel, for instance. And the more you have to drill and the more you have to inject, the more grouting fans you have to make. So this is just purely the amount of holes you have to do. It's not one hole only, but it's the amount of sets of holes. So this is going down in more grouting, more cement needed to inject, harder to seal it. And what you see quickly here, very easily here, is that the altered granite and the Stockholm granite are much harder, require much more grouting than the sedimentary gneiss and gneisses. Makes sense that the altered rocks should require more grouting because you get weakness zones in them. They're more broken apart. But in fact, the altered gneiss doesn't really need that much, which is an interesting thing as well. Then after you grouted this, and then you build the tunnel through it. So you drill ahead of the tunnel when you do this to seal it off, and then you blast the tunnel or drill the tunnel, whichever you're going to do. So after that, you then map the fractures and see which ones are flowing. Are they moist, dripping, or flowing, running? And here we see, again, an interesting thing. The most flowing fractures are, again, in the altered red granite. So they're still hard to seal, even with the grouting. But they're also in the altered gneiss, the most ones. So that makes fair enough sense still. We're in weakness zones. We have more flowing fractures. But the interesting thing is that at least you managed to seal them in the fresh Stockholm granite with the grouting. If we look at these in more detail and break it up by joint set, so orientations again, the important thing to note here is that the shallow dipping, the subhorizontal and the shallow dipping structures, north and south, are the ones that are running. It's the running fractures you really worry about. They're the ones that are just raining in the tunnel and causing real problems, the running water. So that's sort of a data-based effect, and that was sort of a theoretical. I've given you some sort of theoretical background to the fractures and the sort of their orientations, what their patterns might look like on a regional scale, and also talked a little bit about how they're linked to lithology. And now I'm going to show you real pictures of these now, so it's even clearer, hopefully. And first, we'll look at the effect on fracture continuity and orientation. On this picture, this is from just north of here, along E20, the road, right side of the road. We have granite on this side, and we have a nice sedimentary gneiss on this side, on the left side of the picture here. And you can see the contact. You can see the contact by seeing the difference in the fracture network, the fracture pattern. The granite has these, as I mentioned before, very long continuous fractures, quite shallow dipping, and the gneiss has shorter, vertically quite steep fractures that are following the foliation and the gneissosity. But notice they're not so continuous. They're not straight. They're not. You don't have a whole group of them. Like, it's hard to follow one all the way up. Even that's probably the most continuous one there. So they're shorter, and which makes it hard for water to be transmitted. Another picture here down on the E18. It's very easy to see where we have gneiss and where we have granite by the fracture patterns. The gneiss, again, subparallel to foliation. The granite, much more blocky looking. And there you get this big fracture surface right there. You see on the granite right there on the right-hand side. Let's look at a freshly blasted rock here. And again, we see the difference here. We see the gneiss with, in this case, a bit more continuous fractures going and more fractured, which is a little counterintuitive to my tunnel diagram, but which can happen. Anyway, you see these foliation parallel fractures in the gneiss, and then as soon as we get into granite, it just becomes much more blocky and shallower fractures. And all of this I've kind of combined in my head to give sort of a schematic idea of what the fracture patterns look like, or drawings I made of Stockholm granite versus the gneisses in Stockholm. And the key points to take from here are that you have very continuous fractures, often a shallow dipping set as well. They're just very continuous in the Stockholm granite, giving it a sort of blocky appearance. Whereas in the gneisses, particularly in the sedimentary gneiss, the gneissic layers I've drawn here with sort of lighter colored lines. Here's more of a sandy layer. Here's more biotite rich layers. And what you notice is that, see, some of the fractures that try to cross-cut it don't always make it. They get stopped by a change in grain size of the layer, or stopped by a foliation parallel fracture. Now, sure, the fractures that are parallel to the foliation in these biotite-rich layer, like a melanosome here, if this was a melt layer, can be quite open and quite nasty and clay-filled. But they often are. They're not so often that way, and it depends on if you're blasting the rock or if you're drilling in the rock. If you blast the rock, they open up, and so the sedimentary gneiss can be a little bit harder to work in. But if you had a TBM in it, for instance, a tunnel boring machine, these will stay closed. But the main point is to see how these fractures have a hard time cutting across foliation. And it's the same thing if you think about corrugated steel or corrugated cardboard or anything like that. To try to break across it is hard because you have this sort of a pre-existing layering there. And again, this fracture pattern helps you identify these two main rock types from a long way away, as my wife and I like to joke, how to identify rocks from a long way away. It's like a Monty Python reference. But basically, if you're driving by somewhere or you're walking in the forest and you see a sort of flat line, very rounded outcrops with a few long fractures, it's almost certainly a granite or some other massive magmatic rock. As soon as you see ridged outcrops, that means there's probably some layering. It's probably a gneiss. Stockholm granite. Sorry, if you go by a road cut and you see it's really blocky, like in this picture with very long continuous fractures, Stockholm granite. In the tunnel, this more massive continuous fracture kind of and shallow to moderately dipping fractures characteristics of the Stockholm granite can cause some problems. Because in a tunnel, you want to get as good of a horseshoe-shaped contour as possible, because it holds the roof up, the arch the best of the tunnel, just like you want with a bridge, for instance. The more deviations you get from that, the worse it is for the tunnel, let's say. But also, if it's not a perfect arch, that means you've had fallout of the rock that you didn't want to have, let's say. And here you see these little smaller wedges here, but along fairly, longer fractures. Okay, there's still maybe only a couple of meters long here. But on the side here of this tunnel, of this side, you can see quite long continuous fracture here. And in a lot of cases, this might be leading water. In this case, it wasn't, but in a lot of cases, it might. So I'm showing you the Stockholm granite, and then I'm gonna show you the sedimentary gneiss, and you'll kind of compare remember how this looks for the tunnel, and then we'll see it again in the sedimentary gneiss. So now in the sedimentary gneiss, going back to that point I'm trying to make about how the fracture pattern is going to follow the foliation and be steered by it, but you don't get so many continuous fractures. Here you can see the foliation and foliation parallel fractures here, but it's actually kind of hard to pick out ones that are really, really long. You see that one's pretty long, but it gets cut by this one, this cross-cutting fracture. And this is one of the rare cases, or the less common cases, of a cross-cutting fracture that has ease of cutting across the layers. And here it stops that foliation parallel fracture, and that maybe continues on along there. But in general, you see that they're fairly short. It's hard to follow one too long. That one's a bit longer, but then it dies out, and then maybe it hops over to there. And by the way, and I'll show that back in this, generally speaking, fracture patterns in layered rocks are orthogonal. So you get one that goes parallel to the layering, you get one that goes usually almost 90 degrees to the layering in that direction, and then one that's 90 degrees in the other direction. So if you have folded rock in Stockholm, like these big folds in Stockholm, you'll see the fracture patterns bending around these folds. They're following that, and it's not because they were folded, not because the fractures were folded. It's because the layering, the initial layering along which the fractures are going to follow, was folded. To look closer again at the sedimentary gneiss and how hard it is for fractures to go across the layering for long distances. Here we have the foliation here again, and here you see foliation parallel fracturing isn't so very well developed. And also, again, these fractures have a hard time. They're very short. The ones that cross-cut, they have a hard time being continuous. That's probably the most continuous one there, that one here. But even then, you see it hops a bit to the left and the right. So imagine water trying to flow along there. It's kind of hard to do because it's getting blocked every once in a while. It will come across bridges, but it just makes it harder. And if we go back again to the tunnel here, we see we have a pretty decent arch here, quite nice. And that can happen quite a lot in good sedimentary gneiss in Stockholm, if you're in good rock quality and not in a weakness zone or anything like that. It's pretty typical for that. So the foliation here is going across this way. Now, if the foliation was subvertical and going here kind of parallel to the walls, you might have a little bit of a different contour here because you'd probably be getting slices falling out of the wall. So it's not always easy to build in, but it's easier than people think. So that's all I wanted to show about the brittle deformation and the fractures and the fracture patterns that you have in the different lithologies in Stockholm. I just have 2 slides left. And but they're still important if we're going to go about the entire history of Stockholm's geology, the geological history, and we need to talk about the present because it does have bearing on building in the rock, and that is what is the present day stress we have, stress regime in Stockholm look like. And we start out first on the regional scale, or the Finno-Scandinavian shield scale, and basically throughout most of Scandinavia, we have sort of this east-west compression here. This is just the world stress map. And that's caused by the spread of the mid-oceanic ridge. Iceland's pushing the ocean this way, so we're getting pushed that way. So that's the main tectonic driver there. And even when you come down into Stockholm scale, we still have it generally east-west, or we still have it sort of east-west, but it's a bit rotated towards the north. An important part of the point is that because Stockholm is broken up into several blocks, like I showed with those strike slip shear zones, some Bäckström and Chang's model. These blocks all kind of react to that stress differently, and they can bend the stress, and some of them will release some of the weakness zones. They're still moving slightly, will release some of that stress and absorb it, and some of the blocks inside of them will keep stress, and you'll have a higher amount of stress. So if you think of these as sort of stress tensors, the magnitude is the length here. So the longer ones, there's more built up stress, and then we have the directions here and this direction is the main maximum horizontal stress. What is interesting in Stockholm is that we do have high horizontal stresses, which in some is good and bad sometimes. It helps keep your arches in your tunnels if they're oriented in the correct way. But it just means that it's different than a classical modeling and tunneling where you use the main stress is the vertical stress caused by just the weight of the rock. It's not always the case here in Stockholm. But this is the way it looked. This is the most up-to-date one by Catherine Edinburgh and all. It's a Bethel report as well. So that is all I know about Stockholm's geology up to now. But as I said, I hope in the future that we can study more the different generations of the Stockholm granite. I got a feeling that maybe that latest dark generation is not even 1.8 GA. It's maybe something much younger. Look at their geochemistry. Another major unknown is the kinematics of the weakness zones. As I just pointed out, these newly discovered subhorizontal zones. How does that fit into the history, and how does that affect how is that being affected by the current stress regime that you see here? And how does it affect water flow in Stockholm? And also the sedimentary gneiss. As I said, right now it's just a big blue blob on the maps. Step one is to start dividing it into metatexite and diatexite because they behave differently. The diatexite is going to behave more like that Stockholm granite fracture pattern I showed. And the metatexite will be like the gneiss fracture pattern. But also that also probably drives where the sulfides are in Stockholm. So that's another major topic that needs to be researched. But that is all we know now. Thank you for your time.